Morning, folks. How's it going?
It's going good.
That's good to hear. Pretty good, pretty good.
Enjoy green.
Oh, yeah, it's just nice for me, to spend some time with my wife and get out of town for a little while. We had a great time. We went up to Seattle, so it was fun. Hope you guys got rest and maybe
Definitely.
nothing else.
I was at Ensenada, so that was pretty cool.
Oh, wow.
They had like a mission trip. This,
Oh, neat.
yeah,
Yeah,
that's what I was there. Pretty cool.
wonderful. Well, I think I'll go ahead and get it started. As always, it's good to see you all, and I'd like to do our regular opening up in prayer, and then I'll give you a sense of what we're going to cover today. So, dear Heavenly Father, Lord, thank you for the chance to be working with each of the students in this course. Lord, I pray the material that we cover is clear, is interesting, and actually can be enjoyable as we get a chance to see what it's like to be a systems engineer. I pray that this material will help them in their future as they're navigating to the job of their choice. Pray that you'd also help them with their spiritual formation, Lord. Help them all to develop wonderful character. Lord, I pray that you would help them as they get a chance to be studying scripture, to understand all the wonderful things that are contained in the Bible, as well as the theological concepts that we want to derive from that you would help them to cherish them in their heart and to be able to leverage them in their time of need as they go forward. Also give them interesting and creative ways for faith integration. In Jesus' precious name we pray. Amen. Okay, well, we're going to be getting into the last lecture that's the part 3 in our textbook, which is the majority of where a system engineer is really earning their keep is in the concept development. Then there's a kind of an equivalence with the development engineers and the system engineers in the engineering development. And we're going to finish that up today. And then we get into the post-development, the operations, and sometimes you get into production mode. And so with your project work, maybe that would be something that you'll get a chance to be thinking about what that means. So we'll talk about that. And then we're going to be focusing on the next system modeling language, SysML diagram that we're going to be doing, which is the internal block diagram. And so I'll go through another set of lecture notes that talk about that, and then pop up briefly visual paradigms so you can see an example of that for some things that might help you to get an idea of what you might want to cover with your projects. So we're going to be talking about test and evaluation. And so it's the last of these chapters for the engineering development. And so you're thinking about developing things and testing things as a whole. So the objective of the integration and evaluation phase are to integrate the engineering components of a new system into an operating whole and demonstrate that the system meets all the operational requirements. And so you can see a couple of operative things. It's all together, and now you have to test and validate it for the people that are paying for this product. The outputs of the evaluation phase are the validated product design and specifications. So you're going to have the details of the design that are captured in the various design reviews. You're going to have the specifications that give you all of the details. And then you can have the qualification for production and subsequent operational use. So that's going to be important things. The activities that are part of here is you have the test planning, which defines the test issues, test scenarios, and test equipment. So you do that in advance. You have like in a test plan, you would have like expected values or expected ranges, where if it has to fall in that range for it to be a successful test. There's the development system testing that verifies the system meets the specifications. And so when you get in an aggregation, it can be a little bit more difficult to do that and cost more money. We'll talk about that. And then we have the operational test and evaluation. This is where we we get into the validation that the system meets the operational requirements. So a lot of interesting things that have to come together. The closest that you'll see a system just short of being in an operational environment that you have there. So here we have the evaluation phase in relation to the engineering design. So here we can see how we are, everything down to the component level is defined and tested. These are flowing into things that we're going to be doing in the integration and evaluation. If there's a deficiency, then you have to go back out and go back in. So you can have unit failures at system test. I've seen that. It can be a painful process that they have to take a unit off, fix it, and then bring it back in. But that's the whole purpose of why you do system test. You have it all integrated for one last thing. And so this is trying to give you a sense of what that would look like. So in the system test and evaluation, there is a team, an aggregation of a lot of individuals. The system engineer is the technical conductor, if you will, that is monitoring the test, that if something goes wrong, it's his job to go and to ensure that things are brought out to the design engineers. They test it, they retrofit it. You can have times when a unit engineer will actually be brought into wherever the system test is being done. Maybe it turns out there's an interpretation of the results that's incorrect, or finally giving the thumbs up that yes, we have to pull this unit off, we have to do some fixing. So you have the design engineers, you have the system engineers, and then you have the test engineering, the folks that are experts on the testing facilities. All those things have to come together. And you can see with this Venn diagram, you can see that the very center part here is the test architecture. And so you have to be thinking about how you're going to be doing that. And hopefully by the end of this lecture, you'll get a better sense of this. So now we've completed this materialization chart. We've gone through the concept development. We did that earlier. Now this is the tail end of the engineering development where everything is test centric. And so if you pass all the tests, then you're going to say, we're ready to deliver. We have a successful system that is ready to be taken into operation. So here are just some of the things that are part of the system integration evaluation process. We can see now that we're thinking at the system, and so these top level 3 things are related to that. We have the subsystems that have been put together, and the components that are part of each one of those subsystems are all there. So you have real-time operational environment. So this is what you're trying to mimic as closely as possible. You're trying to demonstrate the operational performance. If you don't actually have the ability to do that, so say if you're launching a satellite, you're not going to be able to do that, then you're going to have a simulated environment like a thermal vac chamber. And likely this is going to be in an integrated facility. And if it's extremely expensive to be doing this stuff, it's possible there might be 1 or maybe 2 or 3 of these types of facilities that would be in existence around the country that you would be able to leverage. And so this is, I'll just focus on the system level things here. And so you have the operational test, you have the developmental test, and you have the system integration and test. All of these are things that are taking place in this realm. So in terms of the system element test configuration, so you're going to have the system under test. You're going to have input generators that are going to be putting those things in. You can have the output analyzer that you compare with their test responses versus what you expect. And then we can have a performance comparator, and the test managers are going to say either it did pass or it didn't. And so there's a closed loop way of thinking about how we're doing things in the system test environment. Okay, well, let's think about the developmental system testing, and we'll have a couple of slides that focus on this. The developmental test System test has the objective of verifying that the system satisfies all of its specifications. And I had a chart a couple lectures ago when we had a way of how that can be broken out for the James Webb Space Telescope. You don't test everything. Sometimes it's by an inspection, sometimes it's by analysis, sometimes it's a combination of things. And you want to obtain evidence concerning its capability to meet the operational requirements. The system test environment should be as realistic as practical. So you can't launch a satellite in space to test it. You have to test it on the ground before you launch it. And so this gives you an example. If you have a rocket, you're going to verify it before. A car, you're going to kick the tires and make sure it works before you sell it. A nuclear power plant, all the kind of things that you're doing before it goes operational. There's a lot of checks and balances and things that need to be validated. So moreover, effects impractical to reproduce should be exercised by special test. However, the entire system life cycle should be considered. And so you have to be, you're not going to be having in a test configuration for its whole life cycle, sometimes by exposing it to thermal environments can give you some representation of trying to get infant mortalities out of the way and verify that the system is likely going to last for its full life cycle. Test events must be carefully planned. Related test objectives should be combined to save time and resources, and detailed test scenarios need to be prepared with sufficient flexibility to react to unexpected test results. A predictive test system performance model must be developed. And so I've mentioned this idea of a model-based system engineering. And so this is where stuff we're doing with SysML can actually help out. And so that could be part of this modeling that you have, that you're doing this simulation. This is a major task requiring system engineering, leadership, and effort. However, an engineering development model, EDM, is excellent for this purpose. The development tests are carried out by a coordinated team consisting of system engineers, test engineers, and design engineers. So you might remember this Venn diagram where I was showing you that. Here now we're just thinking about it in more details. The system engineers are who define the test requirements and evaluation criteria. The test engineers actually conduct the test and data analysis. And as strange as it may seem, if they find a deficiency in their mind, that might actually be considered a success, that it's better that they find it then than to have that slip through the cracks and it's in an operational mode and you can't do much about it. Then you have the design engineers who are the subject matter experts that know the ins and outs of those things. And they are who design the test equipment and correct design discrepancies. And so they were shepherding the testing of that and design of that before it was ready for system test. System performance discrepancies during developmental tests must be accounted for in test scheduling, quick responded to by a remedial plan of action. Then in terms of operational test and evaluation, and the next chart will give you an analogy thinking of an aircraft, what it's like operationally versus what it's like in a testing environment. So system operational test and evaluation has the objective of validating the system designs that it satisfies its operational requirements and qualifying the system for production and subsequent operational use. Typical high priority operational test issues are, say you have a new feature that is designed to eliminate deficiencies in its predecessor system. So you can have some special tests that are going to go beyond what you were able to do with the previous block build of what you're having. What are the susceptibilities to severe operational environments? Maybe you find that it's only when you have it at an elevated temperature that you find some sensitivity. That would be good to know now before it's in that operational environment where you have a limited or maybe nothing you can do about it. And interoperability with interacting external equipment. So it's engaging with testing mock-ups of what operational equipment would be doing. Does it interpret that information correctly? Does it perform what it should do? And stuff like that. And finally, we have the user system control interfaces. Interfaces are one of the things that can definitely be something that you want to verify things in this operational test environment. So essential features of effective operational evaluation include, and I think we've got enough here that we kind of have a sense of that. So sorry for the colon at the end of that sentence. So here are, I tried to blow these up to make them a little bit easier to see. So here you can just imagine this is A, and here it's B. So it was a little bit of overlapping here. So here we can think of an operation for a passenger aircraft. And so like my wife and I, we had to get on a plane to go up while we were on spring break. And so I'm sure you've had that kind of a situation. So here's what it's like in the real world. The flight crew, the passengers, the luggage, the fuel, all these have to be loaded in appropriately for a plane. The ambient environment, the flight medium, and the weather extremes, all of those are accounted for in the design. And so if it's rain, you can actually use instruments to help you successfully navigate from your point of departure to your point of completion of your flight. You can be, so it's compatible with the support environment at the airport and the maintenance, and make sure that things are done properly. And so we have the, everything operationally is as expected for the passengers, the luggage, and for the crew. So then you have to think about, well, how are you going to simulate this? So let's assume that we have a completely assembled aircraft that we need to be having. So we need to have the proper inputs, the navigation aids, test crew that are going to be giving you an idea. Does everything check out in the cockpit for the passenger, everything like that? That the fuel is able to be brought into the appropriate places. What I've been told is that the gas tanks are on the wings. And so all those are things that are checked out. You're verifying that you can maintain a temperature in the cabin, that the simulated weather mimics that of what would be seen operationally, and that all of the interfaces that the support equipment that you would have at the airport and for maintenance, all those things are valid. And so then you have the successful outputs of this. You have the measured outputs that you can say that everything is within spec. It performs as we expect. And so thus we can deliver this aircraft into an operational mode. But this is a useful plot to give you an idea, is the relationship between test realism and cost. And we're just thinking for an aircraft. And so what is the level of realism that's necessary for us to, beyond a shadow of a doubt, say that it's performing as required? So if we could be staying down here at the bottom, it's going to be a lot cheaper, but is that going to be enough so that all of the regulatory bodies, the person that's actually buying it is going to be satisfied? Or are they going to be pushing to the ultimate extreme? You can think like the James Webb Space Telescope. With the Hubble, at least you have the potential for servicing it on orbit. The James Webb Space Telescope would be so cost prohibitive to be tested, and I showed you an illustration of where L2 is, where it has in its operational state. So that's a little bit of perspective. So in terms of operational test and evaluation, we have the test planning and preparation. We have the test and evaluation scope, the test scenarios, test procedures, and analysis plan. All of those are things that are laid out. You don't test everything. Sometimes you do things by analysis. There has to be personal training so that you know how you're going to be doing this testing. And so you're going to have testers that are going to be an expert on that. You need the test equipment and facilities. I'll show you in the next chart an illustration of one of the chambers that the James Webb Space Telescope used. And finally, you have the test conduction, you have the test support, data acquisition, human-machine interfaces, and safety, all of those things have to be present. So I found this in one of the articles that I found on the James Webb Space Telescope, and it just gives you an idea. These are individuals, adult individuals, and there's what they're wearing. Sometimes they're called bunny suits. And so literally you're trying to not leave any hair, any skin particles, residue on your shoes. And so they can be pretty elaborate. You can have a smock, which is maybe a lower level of control, but these are a much higher level. And you can just get an idea of the size of the James Webb Space Telescope. And this is a thermal vac chamber. I'm pretty sure that's what this is. And if not, it's just another one of these fancy testing environments that it needs to be utilized to be testing the mirrors, the whole functionality of the James Webb Space Telescope as best we can. We're in a 1G environment, so it has gravity. It's not designed to operate and deploy in gravity. There's a lot of things that you have to do your best to try and figure out how you're going to go about testing it. So in terms of the operational test and evaluation, there needs to be familiarity of the customer or customer's agents, test personnel with the system. And so really you have the customer or the customer's agents that are there through this whole process. They were there probably the early design reviews. They were there at the unit, the subsystem, and now in the system test. And so there's extensive preparation and observation of the development test. Test scenarios make effective use of facilities and test results. So you have some oversight helping out. And this was one of the modes that I acted in various projects that I worked on as a system engineer, acting as a customer agent. Say you have something that's done at a subsystem level that is allocated to someone else. Or I've also been in the mode where it truly is the customer. And as a federally funded research and development company representative, I was part of the team that would be assessing the performance. There's clear and specific test procedures and detailed analyses that are done. There's a thorough training of test operations and analysis personnel. There's the fully instrumented test facilities are in place and validated. There's complete support of the test consumables, spare parts, manuals, etc. There's an accurate data acquisition for diagnostic purposes. Everything that's measured is recorded and archived. There's special attention to human-machine interfaces. Thinking of the aircraft scenario might be a good way to be thinking about that. There's complete provisions for safety of personnel and technical support by system development staff. And finally, timely and accurate test reports. You want things reported out on a quick basis. If the customer agent is not there, you could have periodic reviews of that for a larger audience, and that all of that is stuff that goes on. So there's various kind of test reports. It can be quick look reports, status reports, and the final evaluation reports. So a lot of stuff is going on. So for human factors testing, this was where you can be engaging with displays, controls, and wearable systems. All of those are interesting and are specific for the mission that you're looking at. You can be thinking about your projects and thinking what that would look like for you. So in a couple lectures, I'll talk about the organization that mediates all of the data that comes from the James Webb Space Telescope and all the scientists that are trying to access that and answer interesting scientific questions. These activities that represent requirements across the mission lifecycle phases can be assessed for workload, understandability, and tolerance to error. So if you're like one of your projects looking at an electronic vehicle, you can see what are the interfaces. Are you going to do like an Elon Musk? And so there's a touch screen display. And so almost everything is mediated through that screen. or a more conventional car approach, and how much is actually in your vehicle versus does it have constant communication with resources outside of that. If you have a satellite, you're not going to be anywhere close to that satellite. And so having all of that, those instrumentations and translation of data to a user interface is going to be important. Tests can evaluate different system configuration, workplace layout, or multi-user operations. Okay, I'll probably go through some of this a little bit quicker, but in the test planning and preparation, to actually get to a point where you're in this type of environment, you're ready to push the button and say, yes, we're going to test the James Webb Space Telescope. There's a lot of stuff that has to take place. So this is where it materializes the system as a whole, and you're able to go forward and do that. You're going to have a formal test plan, something called a TEMP, a Test and Evaluation Master Plan, and very detailed procedures. The system's requirements should be reviewed prior to preparing the test plans to allow the customer requirements changing during system developments. And so there can be some change even in this late date. You would hope that that would be minimal because there can have a huge price tag and impact. And so key issues during system integration and evaluation include intense management scrutiny. This is as close as you're going to get to the final product. And so this is why you're going to have that scrutiny. And so having people that have been there not only for this last test is going to be important to try and make it as smooth and agreeable as possible. Changes in test schedules and funding during the development due to development overruns. The James Webb Space Telescope had a lot of delays this way. And you have the standing army effect. You remember early on where I mentioned that system engineering really earned their paycheck early on, where the cost to make changes is not nearly as expensive when it's later in the game. And there's also the readiness of test equipment and facilities. That's going to be something that's going to be looked at for this test planning and preparation. System test equipment design must meet exacting standards, and accuracy must be much more precise than component tolerances. And finally, design must accommodate multiple use and failure diagnosis. So here's just giving us some more thoughts in terms of system development versus test and evaluation. And so this just gives you an idea when you're doing your developmental test versus, full up and running, looking at the test evaluation and planning. And if you're following along with what we have in the textbook, there's a lot of details that need to be thought of. And so I'm not going to get into this, but this is just representative of a lot of things. And if you listen to the recorded lecture that go in detail, that follow in detail the textbook, all of that is explained in those other lectures. All right, well, finishing up with a couple more slides on test traceability. Like I said, everything is recorded. And so there's a huge amount of data that is then turned over to the customer. The testing should be traceable back to the requirements in order to determine if the requirement is satisfied or not. One technique for tracing the requirements to the test is something called the VCRM, the Verification Cross-Reference Matrix, which has every requirement that it has to be meeting, and it will show how it is met, either through testing, analysis, demonstration, or inspection. It can actually also highlight what test, what level, component, unit, subsystem, or system test. All of that is going to be included. You can also have systems of system test. And so this is where we're going to be getting into this in the following lectures when we go beyond just a system. And so instead of just thinking of you're building an automobile, maybe you're building just one silo, maybe you're just looking at a portion of a nuclear power plant, or a satellite that fits into a constellation. Those are all just examples of what you can start to see, that things fit into something larger, a system of systems. Issues involve a larger scale, number of stakeholders, differing objectives, multiple management, and funding arrangements may have competing objectives. And so it's yet another layer where system engineering has to be played. Each individual system within the system of system will evolve at a different rate throughout the system of system development. Other system of system issues that may arise for the system engineer to consider are who is in charge of the system of system test. So is it a consortium? Is it actually a system integrator? Are all system and stakeholders represented in the test? Heaven forbid that somebody is not. But maybe there's some rationale for that. And is the proper data collected and disseminated to all participants? So a lot of information that we've covered in just a few minutes, thinking of the crescendo of doing all of our testing and the validation of what we have with a design. So we looked at the testing and evaluating the total system. We looked at the developmental system testing, then how that folded into operational test and evaluation. We also had a discussion that human factors are important. Ultimately, individuals are going to be interacting with this, and so we need to validate that they work and are going to be useful the way that they're conceived. We talked about test planning and preparation. There's a lot of planning, and so the test planners can reach back fairly early into a program, even though they may not be designing the program, but they're having to lay out in detail the test planning that will be utilized. We also talked about test traceability. We talked about the VCRM. And also we talked a little bit about system of systems testing. Any questions on that? Okay. Let me go on to, now let's talk about the model-based system engineering. And we're going to be talking about the internal block diagram. And so this is where you want to be looking in depth at a block. And so when you're creating a internal block diagram in Visual Paradigms or Cameo Systems Modeler or whatever, that's going to be one of the first things that's going to give you that. And so if we see that in this example here, so here we can see a ABS braking system. And so we have multiple blocks that are included. Now, this is an internal block diagram for the anti-lock controller, which is this block here. And so here, we're just showing two details here. We're showing the detector and a modulator. And so if you've ever heard of a anti-lock brake system, what it's trying to do is you push down on the brake pedal and with all your might, because you want to stop right away. And guess what? That isn't always the best way to do braking. And so it's actually a system that modulates that to give you that optimal braking. So it's like a controller in between the human that's actually controlling the vehicle and the braking system. So that's a first view of what a internal block diagram could look like. And now we're starting to be showing the things. And so in the SysML nomenclature, you would have this IBD with Visual Paradigms. It doesn't always do that. So you start out with that. Then you have the block that you're related to. And then we have these elements that are part of this. And then we can have these ports. We have these connectors. And there's a couple different ways that you can annotate these ports. It can be just a port, or it can be a directional port, or it can be a bidirectional port. And so those are some of the possibilities that you could be having. So maybe just start thinking about what would be something that you would want to drill down at least one more level into what you're doing with your project. And so this is what we'll be digging into more in depth when we talk about this on Thursday. So here is a vehicle system context, and it's also showing the external interfaces. And so here we had an automotive domain, and this is trying to show you that context. And so this is another way that you can be thinking about it. So it's the domain. So the domain isn't just, so you have the car, you have the driver, you have the road, you have the atmosphere. All of these things are related to one another. And so this is a fairly high level way of thinking of an internal block diagram. I would argue that maybe if you're just going to do one or two IBDs, maybe a little bit higher, but that may be something that you might want to think about for one or more of your IBD diagrams that you'll be leveraging. Now this is more focused. Now we're thinking about a power subsystem. And so we have shown other diagrams where we were talking about an automobile, and Freudenthal talks about this. And so what do we have here? Here we have a vehicle processor. We have the engine, the differential, the transmission, the tires. All of these things are being laid out, and you have the fuel tank. So all of these are part of the power subsystem. You need to have the energy that's brought into the engine. You need to have a controller. So instead of just having a fuel injection or a regular carburetor, there's more sophistication in terms of the control that the vehicle processor is doing. And so it's engaging with the engine, it's engaging with the transmission. All of those things are laid out. And so we actually have a module within it, the powertrain. And so you can have some greater fidelity of looking at the contents of a block. These are also some things that are possible. So this is trying to show you the modeling standard ports and the connectors on an IBD. And so you can have like a ball and socket. So this is for a surveillance system. And so we have the user interface and the monitoring station that are what we're thinking about at the next level down from the totality of a surveillance system. And so basically you have a ball is meant to fit into a socket. And so those are some things. So the socket symbol is a required interface specifying a request for services. And the ball is a provided interface specifies provided services. So one is making services available. The other one is requesting services. And so those are things that you can be including in your IBD. So this is a fairly high internal block diagram. So you're just trying to show the gate assembly. You remember we talked about it earlier about say you're in a parking lot and you have to pay before the gate opens. And so here we just have a gate, we have the gate monitor, and we have a sensor. And so those are some things that we have. And then you can start to get into more detail. So now we're thinking about for the control unit. So we have the ticket reader. You have the processor, and there's two inputs to the ticket reader, either a credit card reader or a ticket reader. And there's two outputs. The display unit says, okay, you pass, you're going to be able to get out. And also a printer that you have a receipt for you paid to be able to get out of the parking lot. Those would be some possibilities there. So this is meant to just be an overview. I'd refer you to the Practical Guide to SysML, looking at the chapter on IBD to give you even more examples of things to be thinking about for what you would do here. So internal block diagrams are used to depict the internal structure of a block. The frame of an IBD represents the enclosing block. So if we look at here, this is that whole block that's segregated by those lines. The internal block diagram depicts the usage of a block in a specific context. So maybe it's not every context. Maybe it's just one of the contexts that it's used. It shows how parts and ports are connected, and it shows what flows between parts and ports. So as this isn't an activity diagram, it's just trying to show those interfaces and what flows from what to what. Standard ports are used on an IBD to depict interfaces that specify the behavioral features, that is, the services that a block either provides or requires. Any questions on that? So don't necessarily need an answer, but maybe do a thumbs up if you want. Do you guys have an idea of what you would want to do for an internal block diagram for your project? And if you're still not sure about that, maybe as a result of this lecture, you'll get some ideas about that. Okay. So for today, I'm going to show you two internal block diagrams. And so this first one is a communication system. So I just used a folder here to just encapsulate that. I could have actually done something in a more formal way, like we saw in the sample that we saw here. Like here we saw like a powertrain, but for what I put together so far, this is what I had. And so we have, you can think of how things work for communication systems. You have what's going, you have the information that is modulated, upconverted, and then put, having a high power amplifier. So it's amplified to a high level before it's transmitted. So you have the diplexer here, and then it's sent off the antenna. And then you have the receiver. It goes through the diplexer, and the first thing it does is it's down converted. You have the receiver demodulate. It actually does some basic translation of that information, and then you have a demodulator. So sometimes the receiver and demodulator can be combined, but for this case, I put them in separate modules. I do have these directional ports here. So see if I can. So there's a couple of possibilities for ports. You have a proxy port, a full port, or a flow port. And so these are flow ports, the one that have the arrows on them. And if you put a label on it, just for context, I put on the block diagram that this is associated with. And when you put in these flow ports here, it actually shows up here. There's also some standard ports here. These are ones that aren't flow ports, and so those are also included. And then I'll just quickly show you another one. This is for a power subsystem. And so one or more of you might find this interesting. And I did the same kind of strategy. This is just reference. You don't need to be showing the block diagram, but when you create these different ports, it's going to put them in the proper way. So this is why I use this analogy with something like SysML with a tool like Visual Paradigms or Cameo Systems Modeler. You're creating a database of relationships of information. And so here you can be seeing some of the elements that you would have for a power subsystem. So you have the command module that's telling you what you're going to do. You have a power conditioner. And so say you're having to translate different voltages from one voltage to another, say 28 volts down to 5 volts or something like that. These are bidirectional ports. And so maybe it would have been more descriptive if I had unidirectional ports and then have more descriptive, but I just left it at this point here. So we have the power conditioning, you have the power distribution. So this is what either a wire is connected or not connected to different places. And so you have to power the command module. You're getting the power from the batteries, from the solar panels. All of these needs to be worked out. And then you have the telemetry that's telling you the status of the power subsystem. All of that are the things that you could be annotating for this example. Any questions on that? Okay, well, that's pretty much what I wanted to cover today. On Thursday, we'll continue our discussion about chapters in our textbook, but I'd like to be spending a little bit more time talking about IBDs, and we can do some interactive. You can share what you have, or we can start to develop it real time as we go for there. And I'll show you some examples from Cameo Systems Modeler as well. Okay. All right, well, I think that's a good breaking point, so I'll just shut off the recording there. Thank you.